Welcome back. As promised, this is the fifth and final segment of section 2.1. Uh, so, as I said, this is material that's not covered in the book, but I think that it's an interesting derivation for the cosine of 72 degrees, alternatively the sine of 18 degrees, because it reinforces some of the techniques that for solving polynomials and rational equations that you learned in college algebra, but it's just kind of a demonstration of the kind of complexity that could pop up and why you might need to know that stuff even when this seems like this is all just geometry and relatively simple. So let's move over here and I will set up the kind of the beginnings, just like the previous derivations for exact values. You have to almost sort of create a geometry problem to or a geometric situation where you can actually put the angle that you're interested in some place and be able to find certain values. So let's see, we're on page 9, I think. Okay, so here's how we're going to set this up. We're going to start by drawing an isosceles triangle where the base angles are 72 degrees each. Now, the reason we do that is because the 72 plus 72 is 144, and so the remainder of the angle in that triangle, the apex angle, is 36, which just happens to be half of 72. So I'm going to draw this a little bit large here, and I'm not really great at drawing 72-degree angles, so I'm hoping it doesn't look too weird. But I think that's probably a reasonable. I don't know, it might be okay. So let's say that this is 72 degrees, both of these base angles. And then that makes the angle at the top 36. Okay, so now what I'm going to do is I'm going to actually draw another triangle that is the bisector of this angle right here. And this is where my drawing skills are going to prove to be crap, because if I'd have drawn this correctly, it would look, this should be the same length as this, and I'll kind of demonstrate why. So if you're bisecting the angle, this now becomes 36 degrees, and this is 72 degrees. If this is 72 degrees and that's 36, then this is 108, and this is 36. So just to point out, because the base angles are equal on this triangle, this should be an isosceles triangle as well. So too is this. This is an isosceles triangle. Now I'm going to redraw this because I've got too much crap in here. And I'm going to try to make it just a little bit, try to think how I can do that. I think I need to make it look a little steeper. I think my angles weren't quite steep enough. That looks a little better. So just to point out, the whole triangle is an isosceles triangle. This triangle is an isosceles triangle, and this one is as well. But because these angles, if you look back here, this angle is 72, this one's 72, this one's 36. The big triangles we started with 72, 72, 36. And so if I put some labels on these points, A, B, C, and say D, because the angles are congruent, triangle ABC is congruent, or sorry, is similar to triangle, and let's see, I got to start at the right point, CAD. And so, sorry, I've got a little something in my throat there. So why does that matter? Well, we can bring in the fundamental theorem of similar triangles and start doing some interesting things. So what I'm going to do also, because it's an isosceles triangle, I can just sort of arbitrarily, well, not because it's an isosceles triangle, but I can just set the sides, some side equal to whatever. So I'm going to make the math a little bit easier, I'm going to set this side equal to 2. And because triangle CAD is isosceles, this side's 2. And because triangle ABD is isosceles, this is 2. So all three of those segments are equal to each other, and so I've just arbitrarily picked 2. Now I'm going, since I don't really know the relationship between side AC and DC, I'm just going to call this some variable. Let me just call it X. And so that makes this side over here, segment AB, which should be equal to segment BC, 2 plus X. Okay, so so now I have like some labels for each one of these sides. Now, the fundamental theorem of similar triangles is going to tell me that the ratio of CD to, say, CA, right, so the short side of this triangle relative to the long side, so short side divided by long side, is going to be equal to, in the larger triangle, the short side divided by the long side. So we can write that as an equation. We can say X over 2, so short side divided by long side, long side, is equal to short side divided by long side. So 2 over, and maybe I'll write it this way because it's a little more familiar, X plus 2. So there we have an equation, and it's an algebraic equation. We can forget all about the geometry now, and the task here is to solve for X. Now, you should know how to do this, right? I mean, this is a simple ratio. You cross multiply, and then it becomes a polynomial, and we try to solve a polynomial. So I'll do that in a couple steps here. So X times X plus 2 is equal to 4, right? So cross multiply, and then simplifies to X squared plus 2X minus 4 equals 0. So you can, and you know that when trying to solve quadratics, the first thing you're going to try to do is you're going to try to factor it. Now, after you sit there and waste a bunch of time trying to figure out how to factor that with whole numbers, I'm going to tell you that it's not factorable. The next step in trying to solve a quadratic is to pull out the quadratic formula. And you all probably remember that. X is equal to the negative b, which is minus 2, plus or minus the square root of b squared minus 4 times a, which is 1, times c, which is negative 4. And then the whole thing is over 2 times 1, or 2 times a. Now, the plus or minus always kind of throws people. I mean, algebraically, yes, there's 2 solutions to this, but I can tell you unequivocally that X has to be a positive number, right? I mean, it represents a distance, so it can't be negative. And notice that since the b term, or the negative b term, is negative, if we use the negative branch of the square root, we're going to actually end up with a negative number. So algebraically, yes, there's a solution that is negative, but we don't care about it. So we can only look at the positive branch. And so what this equation reduces to is X is equal to negative 2 plus the square root of, well, that's 4 plus 16, so square root of 20, all over 2. Now, we'll reduce this because this is square root of 4 times square root of 5. Square root of 4 reduces, out comes a 2, and then everything has a 2 in front of it. This actually reduces down to square root of 5 minus 1. Okay, so, all right, that's pretty neat. Now we have the sides of the triangle, and I'm going to go back to the big triangle. So I'll just kind of redraw it there. And you're going to, I think now you're going to see why I wanted to use the number 2 as opposed to 1. So drawing just the big triangle, So remember, its base had a length of 2, and the side out here had a length of 2 plus x. Now, since x is square root of 5 minus 1, this will be 1 plus root 5. Okay, so now we have we essentially have all three sides of this isosceles triangle. And we're going to do the same trick that we did with the 30, 60, 90 triangle, where we're going to bisect this angle at the top. That's creates a right triangle, and it's also the bisector of this line. And so now I'm just and we did that previously. We did it with the 30, 60, 90, but it's true for any isosceles triangle that you do that with. And the result is that we will now have a right triangle that has length of 1 and 1 plus square root of 5. Now, this angle is 72 degrees. And this angle is 18. Now we could find what the length of this side is. We'd have to use the Pythagorean theorem, but trust me, it is not pretty. It will have a nested radical in it. It'll actually have a radical inside of a radical. But this is enough to tell us what the cosine of 72 degrees is, right? Or alternatively, the sine of 18. So recalling cosine of 72 degrees, looking at this triangle at the 72-degree angle, it is adjacent over hypotenuse. So it's 1 over 1 plus square root of 5. Now, that's not simplified because that's, we know that when you have radicals in the denominators, you need to simplify them. And I'm going to remind people of how to fix binomial denominators with radicals. You can't just simply multiply by the square root of 5. You may remember that there's something called this conjugate that you have to multiply. And I'm gonna add an extra adjective to it. I'm gonna call it the radical conjugate. So what we end up doing is we end up multiplying by this ratio, 1 minus root 5 over 1 minus root 5. And that will get rid of the radical in the denominator. So when we multiply this all out, we've got the numerator is pretty easy. It's going to be 1 minus square root of 5. And then the denominator, let's FOIL this out for a second. We have 1 times 1, so 1. And then so that's the first, so we're FOIL, right? And then the outside is going to be a minus square root of 5. The inside is going to be positive square root of 5. And then the last terms is going to be negative square root of 5 squared, which is just negative 5. This is why we did this, because the cross terms, which have the radicals in, are actually, they're opposites of each other and they cancel each other out. So this becomes 1 minus square root of 5 over negative 4. And generally speaking, we're going to get that negative sign out of the bottom just to make it look a little cleaner. This ends up being square root of 5 minus 1 over 4. And just to verify that this is actually true, I'm going to pull out my calculator and I'm going to actually get a numerical approximation for this. So if I take the square root of 5 and then I subtract 1, I end up with 1.23, et cetera, et cetera. Now I'm going to divide that by 4, and there's our number. There's our target number. So we're saying that the cosine of 70 degrees is equal to 0.3090 and some change. Okay, so let's also check that our calculator can take the cosine of numbers any degree we want, and notice it is exactly the same number. All right, so it's an interesting geometry problem. There are some other ones, but of course the algebra starts to get a little bit harder. This is really the limit of anything that we'll do in this class in terms of algebra. Is we do solve some polynomials much later in the semester, and we do a lot of this simplification with radicals in all sorts of different ways. But anyway, so I just wanted you to see this. It's not something I'm ever going to ask you on a test to be able to, produce the cosine of 72 degrees, but it is an interesting exercise. Okay, so this ends Section 2.1, I will see you again in section 2.2.